The recording is on. Yes, so I welcome all of you to this session of thermal engineering, MEC551. Okay, so this morning we're going to discuss something on combustion. Okay, so after this, then we'll move to the last chapter for the semester, which is air conditioning. Okay, refrigeration we have already treated. So after this, then the last topic will be air conditioning system. So in this content of this slide is, we'll be looking at combustion and fuels. So the first thing that comes to your mind when we talk about combustion is fuel, burning of fuel. So we're looking at the burning, okay, and the various composition for fuel, and then apply the conservation of mass to reaction systems. And then we'll also look at how to balance reaction equations. Okay, so we'll be looking at various fuels such as methane, ethane, and so on. So when they react with atmospheric air, what will be the balance equation or the product of the combustion? We'll look into all those details. And then we will have a look at some definitions, very important definitions related to combustion, such as air-fuel ratio and percentage of theoretical air. Sorry. Then also we'll be looking at calculate the enthalpy of atmospheric air, the enthalpy of the reaction. We'll be looking at in details, enthalpy of combustion, and then analyze reaction system according to the first law. Okay, so before we proceed into the chemical equations, there are certain basic definitions that we need to know. Okay, so for example, mole fraction. When we say mole fraction, it is mathematically, it is the number of moles of a particular species. For example, let's say if I have in a particular system, thermodynamic system, I have number of moles of oxygen to be NO, and number of moles of nitrogen to be NN, and I have, let's say, number of moles of hydrogen to be NH2. Okay, so if I want to find the total number of moles of this element, the total number of moles in the mixture equals to N oxygen plus N hydrogen plus what? N nitrogen, like this. So that's the total number of moles. And if I want to find the mole fraction of hydrogen, for example, it is going to give me Y. So by definition, mole fraction of hydrogen is going to give me this, moles of hydrogen, which is equal to the number of moles of hydrogen divided by the total number of moles of the mixture. That's it. So similarly, if I want to find the number of moles of oxygen, it is going to give me N oxygen divided by the total number of moles in the mixture. Okay, so this is how we estimate mole fraction. Okay, and then also mass fraction is the same. If we represent this by mass of oxygen, mass of hydrogen, and mass of nitrogen. Okay, so if you want to find individual mass fraction, it is given by MF. That's the mass of the individual component divided by the total mass. Okay, now in reaction, combustion, the total molecules and mass, okay, equals to the sum of individual components. Say, if I want to find the total number of moles of oxygen, hydrogen, and nitrogen, just sum them. Similarly, the total number of mass for the individual component, you just sum. So mass of oxygen plus mass of hydrogen plus mass of nitrogen, like that. Okay, So then a very important definition also here, we have molecular weight. So this is a recapitulation of what you did in your previous elementary secondary chemistry. Okay, so molecular weight is a parameter which is a measure of the mass divided by number of molecules or number of moles of a species. Okay, so molecular mass equals to m, small m, which is the mass, divided by the number of moles. All right, so now we can express this equation again as m can be represented over here. M can be represented by capital M times N. Okay, so which is equivalent to this. Okay, so we represent M by Mn. So which is this? So Ni, Mi. So divided by total number of moles. So if you look back in the previous slide, Ni divided by N gives us the mole fraction. You understand me? So mole fraction times the molecular mass gives us again the mass like this. So this is the mass, the mole fraction of individual species like oxygen. So let's say molecular mass of oxygen equals to the mole fraction of oxygen. That is the molar mass of oxygen, like that. Now we come to ideal gas equation. I think most of you are familiar with ideal gas law. PV equals to MRT. Okay, so by definition, ideal gas constant equals to universal, this is what we call universal gas constant. Universal what? Gas constant. Universal gas constant. Okay, it is a parameter which is constant. So, and it is given by 8.314 kilojoules per kilomole per Kelvin. It's a universal gas. It means it is constant everywhere you go. But this ideal gas constant, R is what we call ideal gas constant. This ideal gas constant can change depending on the type of gas you are talking about. Let's say if you have ideal gas constant for oxygen will be different from ideal gas constant for hydrogen. Also, we have ideal gas constant for, let's say, nitrogen. You understand me? So these quantities will be different from each other. And the universal gas constant is constant everywhere. So if I ask you to estimate the ideal gas constant for oxygen, if you know the molar mass of oxygen, then it means that the ideal gas constant for oxygen equals to the universal gas constant divided by the molecular mass of oxygen. You understand me? Similarly, ideal gas constant for nitrogen gives me the universal gas constant divided by molecular mass of nitrogen, like this. Okay, so you have to pay attention to that. Now we come to what is combustion process, or what does that mean? Combustion means it's a chemical reaction during which a fuel is what? Oxidized. So when we say the word oxidize, oxidation is the process of adding oxygen to a particular species or a particular reaction. Okay, so that is oxidation reaction. You understand me? So it's a reaction between oxygen and another compound. Okay, so in the realm of combustion, so whenever a fuel is oxidized, means that fuel is burned in the presence of oxygen, a large quantity of energy is what is released. So the energy can be viewed as the ability to cause change, okay, which is according to the first law of thermodynamics. Okay, the chemical composition and the thermal energy release during a combustion process is this. So this is an example. So here we have carbon and oxygen. When they come together, they react in the presence of heat. So then it releases carbon dioxide and thermal energy is given out. You understand? So large amount of energy is released in combustion process. Similarly, if we combine carbon dioxide with atmospheric air, later on we'll get to know that this composition is related to atmospheric air. So oxygen and nitrogen combined is an atmospheric air. All right. So this gives us carbon dioxide, nitrogen, and some heat is liberated. Okay. So this is a combustion reaction because carbon is being reacted with air, and it gives some product of combustion and heat. So the above equation we call as chemical reaction equation. So now let us look at fuel and the various types of fuel. Any material that can be bent to release thermal energy, okay, is a fuel. Okay, petrol, benzene, okay, diesel, okay, and natural gas, LNG, LPG, propane, all these are fuel. So most familiar fuels are hydrocarbons. Hydrocarbons are fuels that are made up of carbon and hydrogen. You understand me? So carbon and hydrogen, or hydrogen and carbon. They are denoted by CnHn, HM. The hydrocarbon fuel exists in all phases. So means that we can have fuel existing in solid state, liquid state, or gaseous state. You understand? As you all know, coal is an example of a solid, and gasoline, petrol is oil. You understand me? So and natural gas, LPG, LNG, all this. So application of fuel or combustion can be found in generation of electricity, transportation, in our vehicles like this, industrial production lines, they all need oxygen. Oh, sorry, combustion process. Now, there are various types of fuel, okay, together with their ignition temperature. So, for example, if I have gasoline, the ignition temperature for gasoline is 260 degrees Celsius. Means that gasoline will only burn when it reaches this temperature. When the temperature is below 260, there will not be any combustion taking place. Similarly, carbon, also the ignition temperature is 400. And hydrogen, ignition temperature is this, followed by methane and so on. So before these fuels can be burnt, you need to reach minimum these temperatures. You understand? So now let us look at oxidizer. When we say oxidizer, we are referring to oxygen because oxygen is the main component which involves in oxidation when it comes to combustion reaction. You understand? So now an oxidizer is a type of chemical which a fuel requires to burn. You understand me? The source of oxygen. So when the fuel burns with oxygen, then the oxygen becomes the oxidizer. So the oxidizer most often used in combustion processes is air. You understand me? So we all know that when you want to burn a fuel, you just, in the presence of small amount of heat, then there will be ignition taking place. Okay, for example, in your motorcycle or in your vehicle, might be Produa or something like that. So in the cylinder where the combustion takes place, air is coming from the atmosphere. So the air comes into the carburetor and then it is injected into the cylinder. And when the fuel mixes with the air, atmospheric air, so when there is ignition, spark plug ignites, then there will be combustion taking place. You understand me? So the main oxidizing agent over here is the oxygen. However, pure oxygen is used as an oxidizer only in some special applications, such as cutting and welding. So sometimes if you go to the Benkel, the workshop where they repair auto bodies, Maybe they need to cut a particular metal, and then they use some cutting flame. You see that they will use some flame for cutting. So that flame, they have a large bottle of, very large bottle of oxygen, which is stored in the container. And it is this oxygen, pure oxygen, which is used for the generation of the burning or the oxidizer in order to proceed with the cutting and then the welding. Okay, there are no, therefore, in order to make a combustion occur, it must consist of fuel plus atmospheric air. You understand me? So for combustion to take place, we need the presence of fuel. There should be air, and then we have our product of combustion. If you remove the air from the fuel, there will not be any combustion. If you remove the fuel from the air, there will not be any combustion. So both of them has to be put in place. Okay, so over here, air is the oxidizer, where for this equation, oxygen is the oxidizer over here. Okay, so now we come to a very important concept. Pay attention carefully. So let's say atmospheric air is composed of, we all know, if you take any sample of atmospheric air, okay, that sample of atmospheric air will contain some percentage of oxygen, and that percentage of oxygen is 20.9%. And then it will contain some percentage of nitrogen also, and let that percentage be 78.1%. And then it will contain some percentage of, let's say, argon or nitrogen. Okay, so these are what we call inert gases. So the inert gases, normally, they don't react during the combustion process. They just come in and then go out. They come in and then go out. So these are what we call the inert gases. Inert gases. They don't undergo any reaction. So an example of inert gases is nitrogen and argon. These are examples. Okay, so we classify that these inert gases consist of 0.9%. So very, very, very small. Okay, so in our analysis of combustion, we assume that oxygen forms 21%. We approximate this, you see, we approximate this to become 21%. And then nitrogen also consists of 79%. So nitrogen is very, very large. It forms a very large percentage. And then this is argon. So since the argon is treated as nitrogen, it means we add it to this nitrogen because it is very, very, it is insignificant. The argon is insignificant. You understand me? So it is insignificant. So we just add it to the nitrogen, and then it becomes 79%. You understand me? So whenever we talk of atmospheric air, then we should know that from today, we will be thinking about oxygen and nitrogen only. We will not consider argon. So these are the composition of atmospheric air. So the atmospheric air consists of 21% and 79% nitrogen. Okay, so now let us see. Therefore, each mole of oxygen entering the combustion chamber is accompanied by 3.7 mole of nitrogen. Look over here. Let's say I've told you if we have in atmospheric air, we have 21% oxygen and 79 nitrogen. So for every 1 mole of atmospheric air, or say, let's say for any amount of atmospheric air that enters the combustion chamber, it will be accompanied by, let's say, if I divide, I'm dividing, let's say here over here. So we have the atmospheric air consists of, we have oxygen. Let me delete this, so then it will be clear to everyone. Okay. So we have, let's say, atmospheric air consists of oxygen and nitrogen. The percentage of oxygen is 21%, and percentage of nitrogen is 79. Okay, percent. So now, if we want to express this, I divide this by 21. I divide this by 21. This is going to cancel. So this gives me one kilo. I'm going to have 1 kilomole of oxygen. Sorry, 1 kilomole of oxygen. So I'm going to have 1 kilomole of oxygen. Oh, so everything is gone. So let me write over here instead. So I have oxygen and nitrogen. So this is 21%, and this is 79%. So I divide this by 21%. I divide this by 21%. So this gives me 1 kilomole of oxygen in 1 kilomole of oxygen, and then that gives me, this one gives me 3.76 kilomole of nitrogen. So in every amount of atmospheric air, there will be, for every 1 kilomole of oxygen present, there will be 3.76 kilomole of what? Nitrogen. It's just like, let's say, if some students, let's say we have a class, okay? So, or let's say we have a team, and team A, for every team, let's say we have team A and team B. For every 1 female in this team, there will be 3 students. Sorry, there will be three male. You understand me? So for every 1 female present in the team, there will be 3 male. Similarly, for every 1 female that you see in the team B, there will be 3 male. You understand me? So this is the composition of each particular class, like this. So the same thing applies to atmospheric air. For every mole of atmospheric air that you take, there will be 1 kilomole of oxygen, or for every 1 kilomole of oxygen, there will be 3.76 times kilomoles of nitrogen. So that's the meaning. You understand me? So now the total number of moles of the atmospheric air becomes 1 kilomole plus 3.76 kilomole of nitrogen. So this is for the oxygen, and this is for the nitrogen. And this gives us 4.76 kilomole of atmospheric air. You understand me? So for every 4.76 kilomole of atmospheric air, there will be about three more of oxygen present. You understand? So that's the concept over here. Now let us look at the chemical balance. Okay, these are just basic chemistry, balancing of equations. So the chemical equations are balanced on the basis of conservation of mass principle or mass balance. Okay, so mass balance, for mass balance, the total mass of each element is conserved during a chemical reaction. I'll explain. Okay, so assuming, for example, I have 1 kilogram of fuel, 1 kilogram of fuel. It can be petrol, it can be not which type of fuel you can think of. And then it is accompanied by 17 kilogram of air. So this is the mass. So mass of fuel equals to 1 kg, and mass of air also 17 kilogram. If both of them enters this combustion chamber, the total mass of the product is going to be 18 kilogram, because we have 1 plus 17, and that gives us 18 kilogram. So here we say mass is always balanced. The mass of the reactant and the mass of the product have to be the same. So the total mass of each element in the product equals to total mass of each element in the reactant. Okay, so total number of atoms of each element is also conserved. Total number of atoms. For example, the total number of atoms in the reactant equals to total number of, when we say total number of atoms, it is the same as total number of elements. Okay, but the number of moles is not conserved. For example, let us see in this equation. Here we have in the reactant side, this, when we say reactant, this is reactant. And this is product. This is product. So at the reactant side, how many atoms do we have? Can somebody tell us? How many atoms or how many mass of element do we have? Carbon is 1, and oxygen is how many? Oxygen is 2. So the total gives us what? 3. The total number of atoms in the reactant is 3. What about the product? Here we have 1 carbon and 2 oxygen. So again, at the product, the total number of atoms equals to 3. So you see that the number of atoms, both reactant and then the product is balanced. You understand? So that's the concept. But the total number of moles is not always conserved. Let me show you what we mean by that. So the total number of, here I have 1 mole of carbon, and here 1 mole of oxygen, and here I have 1 mole of what? Carbon dioxide. So at the product side, how many moles do we have at the reactant side? Here we have 2 moles or 2 kilomoles. Whereas at the product, we have what? 1 mole of the carbon dioxide. So it is not always necessary that the total number of moles has to be conserved, but the mass has to be conserved. The number of atoms also need to be conserved. You understand? So that's the concept here. So now we come to other very important definitions as well. We have air-fuel ratio. Air-fuel ratio is the ratio of the mass of air divided by mass of fuel. So if you know the mass of air entering a combustion chamber, for example, you have a combustion chamber, air is coming in, and then we have fuel also coming in. If you know the mass of the air, you know mass of the fuel. The ratio of these two is given by mass of air divided by mass of fuel, is called the air-fuel ratio. And fuel-air ratio, FA, this is AF, air-fuel ratio. Fuel-air ratio is the mass of fuel divided by mass of air. Okay. So now, as we have already seen in the previous slide, the mass of air is the number of moles times the molecular mass, okay, of the fuel. And also, very important thing we need to know also over here, frequently, these are the frequently used properties. So mass of air, mass of atmospheric air is 29 kilogram per kilomole. And mass of hydrogen is 2 kilogram per kilomole. And mass of carbon is always expressed as 12 kilogram per kilomole. So all these are available in the property table as well. So you need not to worry so much. Okay, so then another very important definition, equivalent ratio. Equivalent ratio is the ratio of, is expressed by phi. It is the ratio of air fuel ratio for actual reaction divided by air fuel ratio for stoichiometry. Later I'll explain what is meant by stoichiometric air fuel ratio. Okay. Now, we want to look at what do we mean by complete and incomplete combustion. So this is very, very, very important. A complete combustion means all complete combustion occurs if all the carbon that is present in the fuel is converted or burnt into carbon dioxide. So it means that all the carbon present in the fuel is converted into carbon dioxide. This is called a complete combustion. And all the hydrogen that is present in the fuel is also converted into water. So these are the conditions for a complete combustion of fuel. And similarly, all the sulfur, if all the sulfur present in the fuel is also converted into sulfur dioxide. So these are the priority, these are the three main. So if they ask you, what are the conditions for a complete combustion of a fuel? So all that you need to mention, when all carbon is converted into carbon dioxide, hydrogen is converted into, is burnt into water, and then all the sulfur is also burnt into sulfur dioxide. So these are the primary information which is needed for complete combustion of a fuel. All right. So now incomplete. So then what do we mean by incomplete combustion? So incomplete combustion occurs if the combustion product contains any unburnt, so you see, underline the word unburnt fuel, or components such as carbon, hydrogen, carbon monoxide, hydrogen peroxide are present in the product. You understand? So if any of this is present in the product, then it is incomplete combustion. You understand? So it means that all the carbon is not converted into carbon dioxide, and all the hydrogen is not converted into, it's not burnt into water. You understand me? Okay, so and so on like that. So reason for incomplete combustion, we can ask you in exams, what are the reasons for incomplete combustion? One of them is insufficient what? Oxygen. Sometimes you see that if you pile up some rubbish, let's say you pile up some firewood and then you want to set it into fire. What do you observe? Initially, if you put the flame inside, you see that there will be some white smoke. There will be some smoke coming out from the there will be some smoke coming out from the pile up of the rubbish. So the smoke is coming out because there is no sufficient oxygen for the fire to start. So that's why that is called incomplete combustion. You understand me? And also, sometimes you see that when you are driving your motorcycle, the exhaust So the exhaust from the motorcycle will be discharging some whitish, let's say some blue or whatever, light blue or dark flame. You understand me? So, sorry, it could be discharging some gases at the exhaust. Okay, so those gases, the color could be like blue color or light blue. You understand me? So, these are the condition. This condition is telling us that there is incomplete combustion inside the cylinder of the motorcycle. Okay, so it is incomplete combustion. Okay, so means the motorcycle or the lorry need to bring sufficient oxygen coming from the carburetor into the combustion chamber. All right. So another issue also is that we have insufficient mixing. So an example is this. So because the rubbish is piled up, it does not give way for oxygen to penetrate or atmospheric air. So there will not be a sufficient flame until eventually you see that when you spread the rubbish, now the fire will catch the whole, what do you call it, pile up of the rubbish. Okay, another third condition is that dissociation at high temperatures. Okay, so dissociation at high temperatures means that if, let's say, at a very, very, very extremely high temperature, okay, when the flame reaches the dissociation temperature for the oxygen, instead of the oxygen reacting with the fuel, it will instead dissociate. You understand me? So dissociation means that it will react to form a different component instead. You understand? So that's the concept. So these are the three primary conditions which causes incomplete combustion. Take note of this side. It's very, 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 very important. Okay. Next, we look at, yes, the areas we have reached now. I'll encourage you to be pay attentive. Okay, pay attention to this. Very, very important. We want to look at what we call stoichiometric. Stoichiometric. What do you mean by stoichiometric? Stoichiometric is the minimum amount of air needed for the complete combustion of fuel. Understand? Minimum. That's the minimum amount of air for the complete combustion of a fuel. It's called stoichiometric. All right? And it is also referred as 100% theoretical air. Okay, 100% theoretical air. So the ideal combustion process during which a fuel is burnt completely with theoretical air is called theoretical combustion. You understand? So the word stoichiometric. So, gentlemen, please, can you mute your mic? Okay. So let's proceed. Yes. So the word stoichiometric means the exact amount of air which is necessary for complete combustion of a fuel. Similarly, so in the previous example, let's say we have an example over here. However, in actual practice, excess air is supplied in order to ensure complete combustion. So this is an example of complete combustion of a fuel, because what are the necessary conditions for complete combustion? All the carbon should be converted into carbon dioxide. All the oxygen should be converted into water. Now, nitrogen, pay attention, gentlemen. The nitrogen is an inert gas. It always comes in and goes out. It does not participate in any reaction. So this is a complete what? A complete combustion. It's a complete combustion because it fulfills all the conditions necessary for complete combustion. All the carbon is converted into carbon dioxide, all the hydrogen is burnt into water, and then we have there, and the nitrogen comes in, nitrogen goes out. So, but what we are saying over here is that in order to ensure complete combustion, all the time we put some excess air. Excess air is more air is put into the combustion to ensure the complete combustion. So, in complete combustion process, in complete combustion process, there are certain criteria we need to follow. We have to set the number of moles of the fuel to be equal to 1. So this is for balancing. I'll say it's for balancing of the fuel. Okay, or let's say balancing of the combustion process. Combustion reaction. Okay, so one of the conditions is that you need to set the number of moles of the fuel to be equal to 1 and assume the possible substances in the product. For example, here, these are the possible substances in the product: carbon dioxide and water and nitrogen. You understand me? So write down the known mole numbers in the fuel, air, setting, and setting products, and set the unknown mole numbers with letters. So I'm going to describe all these things by taking an example later on. And then we have to balance carbon dioxide, carbon monoxide, carbon with the number of carbon from the fuel, and balance water, hydrogen or dioxide, hydrogen peroxide, hydrogen peroxide, and then hydrogen gas, and then hydrogen atom from the fuel. Okay, so we need to balance the oxygen also like this. Okay, so but we need to know that for every the number of moles of oxygen, for each mole of oxygen present in air, there will be 3.76 mole of nitrogen. Just like in this class, if I say that for every, let's say if I want to find the distribution of the male student and then the female student. So if I say for every female student that I take, there will be 3 students. There will be 3 male students. So this is the composition. This is the composition of the distribution of the student in the class. For every 1 female student, there will be 3 male students. So the same thing we are talking about here. That is 3.7 times, 3.76 times of nitrogen present in the air. Okay, so that now, if the air is used instead of concentrated oxygen in the reactant, then 1 mole of oxygen in the air will accompanied by 3.7 mole of nitrogen. So it's the same thing. All right. So now we almost finished with that this portion. Very important areas. Now we come to the main combustion process. Like I've told you, excess air is the term used when combustion air is supplied greater than the stoichiometric air. So what do we mean by stoichiometric? Stoichiometric is the exact amount of air, the exact amount of air which is necessary for a complete combustion. However, if you want to ensure that your combustion proceed with complete combustion, you need to add excess air. You understand me? So when we say 0% excess air is equal to, it is the same as 100% stoichiometric air. And when we say 50% excess air is the same as 150% stoichiometric air. You understand me? So 0% excess air, this is the standard. 0% excess air means that I'm putting 100% stoichiometric. And this is the exact amount of air which is necessary for a complete combustion. But if you want to ensure that, or if you want to put some more air into the combustion process, then you can increase the amount of air. Means this is 50% excess air. Here, 0% means I'm not putting any excess air. So, but 50% excess air gives me 150% stoichiometric air. So if I have, let's say, 80% excess air, then it is going to give me 180% stoichiometric air. Okay, so normally we refer, whenever you have 150% stoichiometric air, we refer to it at 1.5 kilomole. And 180 stoichiometric air, 1.8 kilomole of the air. We will look at some equations later on. Okay, now the next thing, if the combustion air is supplied less than the stoichiometric, assuming you starve the fuel. Starving the fuel means that you remove some of the air from the fuel. So it means that you are starving the fuel. So starving the fuel means the combustion process, and you have, it means the air is supplied less than the stoichiometric amount. It is termed as air deficiency or starved air. So for example, 10% starved air is equal to 90% stoichiometric air. You understand me? So it means that if we starve the air by 10%, it means out of this 100, we try to remove, we take out 10%. So then there will be 10%, 90% stoichiometric air. Okay. Now, looking at the first law of thermodynamics, we all know this equation already. It's very, very familiar with this equation. Okay. From the first law of thermodynamics, it says that the net heat added to a system minus the net work equals to the change in enthalpy of the system. Okay, that's the change in internal energy of the system. Okay, and that this is under for first law. You understand? For a control volume, of course, for a control volume system. All right. So this equation can also be considered as the net heat added to a system minus the net work should be equal to the change in the enthalpy of the product minus the enthalpy of the reactant. So P here means product, and this is the enthalpy of the reactant. Now, in any energy analysis, standard reference is defined as 20 degrees Celsius and 1 atmospheric pressure. The property value at the standard reference state is referred to as this is standard. So whenever you see HO, SO, UO, you understand me? These are properties that have been read at standard reference state. And standard reference state means that it is at 25 degrees Celsius and 1 atmospheric pressure. For example, if I ask you, what is the enthalpy of steam? What is the enthalpy of steam at standard reference state? So it means that I want you to tell me the enthalpy of steam at 25 degrees Celsius and 1 atmospheric pressure. And so then you have to go to the property table and then you tell, okay, the enthalpy of the steam equals to, and then you read for me. Similarly, the entropy at standard reference state, internal energy at standard reference state is also given by this. All right, so then again we have HR. So enthalpy of reaction. Difference between the enthalpy of the product at the specified state and then the enthalpy of the reactant at the same state in a complete combustion. Okay, so the enthalpy of reaction is the difference between the enthalpy of the product. Enthalpy of the product, so means HR equals to enthalpy of the product, okay, at a specified state. And then the enthalpy of the reactant at the same state in a complete reaction. Okay, so like that. Okay, so now here is it. Enthalpy of combustion also is given by enthalpy of the product minus the enthalpy of the reactant. Okay, so at a given state. Now, this equation can also be referred to as, now also we have enthalpy of formation. Yes, very important. Enthalpy of formation is the enthalpy of a substance at a specified state due to its chemical composition. Later, we will come to know all these things later. Okay, so enthalpy of combustion can be represented by the Q, the heat added, or the heat liberated because of the combustion, and is equal to the enthalpy of the product minus enthalpy of reactant. Okay, now this can be represented by this equation. This is the number of moles of the product. This is the enthalpy of formation of the product minus number of moles of the reactant, enthalpy of formation of the reactant. Okay, normally nitrogen, oxygen are considered as stable elements. Thus, their enthalpy of formation is equal to 0. Okay, be careful over here. You see that nitrogen and oxygen, they occur in their natural states. They are natural. You cannot form oxygen. Oxygen is oxygen. You cannot form it. It occurs in its natural state. So the enthalpy of formation of oxygen is equal to 0. Enthalpy of formation of nitrogen equals to 0. But enthalpy of formation of carbon dioxide is not equal to 0. Why? Because carbon dioxide is formed from carbon. If you have carbon plus oxygen, that gives you what? Carbon dioxide. You understand me? So this carbon dioxide does not really exist in its natural state like this. It is formed by the combination of two elements, namely carbon and oxygen. So its enthalpy of formation is not equal to 0. But the enthalpy of formation of nitrogen is 0, enthalpy of formation of oxygen is 0, because they exist in their natural state at that point. Okay, so now analysis of combustion reaction. In actual combustion process, the temperatures of the reactants and the products are not at standard reference state. So in all practical life situation, you see in our combustion, internal combustion engine. So the temperature is very, very high, extremely very, very, very high. So we cannot bring that particular state, or we cannot refer to it as a standard reference state. So standard reference state implies it is the property of that fuel or the property of that substance at 25 degrees Celsius and 1 atmospheric pressure. You understand me? So, but here we are saying that in actual combustion process, the temperatures of the reactants and the product are not at what? Standard reference state. Then the enthalpy of the enthalpy value of the reactants or the products are evaluated at evaluated temperatures. States can be expressed by this. So the enthalpy of the reactant equals to, so this is very important. In final exams, most likely you will have questions where you need to use this equation. Okay, so the enthalpy of the reactant equals to the number of moles of the species of each. So let me explain it very clearly over here. So for example, we have enthalpy of reactant. equals to sum of the number of moles in the reactant times enthalpy of formation, okay, at standard state, plus enthalpy at a given state, that is HT, and then enthalpy minus enthalpy at standard state. Okay, so let me explain. So HF, it is very important that you understand this. So HF, Ni is the number of moles. Ni equals to number of moles of what? Each element or species. And HF, when we say H dash, H dash 0, F, this is the enthalpy of formation. Enthalpy of what? Formation at standard what? At standard state. Why is it standard state? Because of this 0, because of this. Okay, enthalpy of formation at standard state. And HT is the enthalpy of that element at the given state. Means that, so if I say enthalpy of formation at standard state, means at standard state means at 25 degrees Celsius and what? 1 atmospheric pressure. Okay, so allow me to delete this, then I'll define again, I'll define HT. So HT, we are again looking at this. HT is the enthalpy at the given state. Enthalpy at the given state means that it could be at any temperature apart from 25 and 1 atmospheric pressure. It could be the enthalpy at, let's say, at 80 degrees Celsius, at 90 degrees Celsius. You understand me? Sorry. So HT, so enthalpy. So it could be enthalpy at given state. So means it could be at, let's say, 30 degrees Celsius, at 40 degrees Celsius, and so on and so forth. Any temperature apart from 25. You understand? That's the enthalpy. And then we have, again, the other one, the last one. So this is very important, ladies and gentlemen. We have HO. This is the enthalpy. This is the enthalpy. This is the enthalpy at standard. Enthalpy of the element at standard what? At standard state. At standard state means at 25 degrees Celsius and 1 atmospheric pressure. What is the difference between this H and HF like this? This is enthalpy of formation. This one is enthalpy of formation, and this is the enthalpy, and this enthalpy of formation at standard state. And this is the enthalpy of formation only. Sorry, and this is the enthalpy. This is the enthalpy at standard state. This H is the enthalpy at standard state, and this is the enthalpy of formation at standard state. Okay. All right. So now let us proceed. So now we have the enthalpy of C carbon and oxygen is assigned to be 0. Why? The enthalpy of formation of carbon and oxygen, because at standard reference state and 1 atmosphere pressure, it is designated as HF or HO. Okay, so let's say we have a reaction between carbon and oxygen, and that gives us carbon dioxide. Okay, so we are forming carbon dioxide over here. So it means that the enthalpy of the combustion equals to the enthalpy of the product minus the enthalpy of the reactant. So the enthalpy of the product is the carbon dioxide minus the enthalpy of the reactant, which is carbon and oxygen. So that gives us minus 39352 kilojoules per kilomole. Okay, so these are various property for fuels at various standard states. Okay, so if you take something like pentane, okay, C3H18 is enthalpy. So the molar mass of the fuel is this. The enthalpy of formation is this. And then carbon dioxide molar mass is this. Enthalpy of formation is this. And then water also is molecular mass is this, and enthalpy of formation is this. You see that here, the molecular mass for oxygen is this, but the enthalpy of formation is 0. This also 0. Why? Because they exist in their original states at this state. Like hydrogen is also the same. Okay, and this is their change in their enthalpy. Okay, so I think I have come to the end of the discussion for combustion. So I'll just spend some time to discuss just a few simple questions, and then we'll postpone our class to the next class, that is after the holiday. Is there any questions so far till now from anyone before I look into some simple question? So my friend, anybody, any question? Amir? Yes, any question? Say it. Any question from anybody? All right, so I'll move on to, let me see, I have a question over here. Okay. Yes, so here we are told that, let me see. Yes, develop the combustion equation and determine the air-fuel ratio for the complete combustion. There's a noise in my, can you hear me clearly? Is it clear? My voice, is it clear? Can you see my slide also clearly? All right, all right. All right, so now in this question, let's say A, theoretical A, theoretical A. So first thing we need to do is to balance the equation. So when we say theoretical air, it means that, what do you call it? It implies that the exact amount of air which is required for the complete combustion of the fuel. And what are the necessary conditions for the complete combustion of a fuel? Here we have carbon. The carbon, all the carbon need to be burnt into carbon dioxide. And similarly, all the hydrogen need to burn into what? Into water. The water will be the product. And then the nitrogen in the fuel, okay? Sorry, the nitrogen in the air will just come out like that without participating in any reaction, okay? So when we say theoretical air, it is the exact amount of air which is necessary for the complete combustion. So we're going to write down the equation down. We have C for H10. This is the fuel plus air. So the air is this. Now the air consists of oxygen. For every 1 mole of oxygen, we will have 3.76 moles of nitrogen. You understand me? So this is the air. That's the atmospheric air. This is the air. So it's very important that you understand this. So this is the air. Okay, but since we don't know how many moles of air is used in the for the reaction, we need to calculate that. We name it Z, the number of moles of air which is used, okay, for the complete combustion. That's what we don't know. Okay, that's what we want to calculate. Okay, so now the reactant at the reactant side, okay, so we are going to get what are the product. So on the product of the combustion, all the carbon will be converted into carbon dioxide. So we have CO2. And then the water will also be converted into, sorry, the hydrogen will be converted into water. And then the nitrogen just goes in and comes out. So then you have plus nitrogen over here, nitrogen. Okay, so now, since we don't know how many moles of the products, carbon dioxide, water, and nitrogen is there, we can represent them by, let's say, we represent this by A, this will represent by A, this will represent by B, and this will represent by Z. So we are going to balance the equation now. So balancing the equation, we will take them one by one. We will take carbon first. So carbon, balancing of carbon, balancing. So balancing of balancing of equation. So we have carbon, okay? And the product side, sorry, reactant side, how many carbon do we have? 4. So that's all, we have only 4 atoms. And this equal to, how many carbon do we have over here? We have A, so 1, so which is A. So this should be equal to A. So means A equals to 4. You understand me? So A equals to 4 in this particular equation. So then we move on to hydrogen. If we balance hydrogen, how many atoms of hydrogen we have? We have 10. at the reactant side, and then the product side, we have hydrogen 2 over here times B. So we have 2B. So now this gives us 2 divided by 10. This gives us B equals to what? 5. Okay, I hope you are following what I'm doing. Now we come to the oxygen side. Very important. Oxygen. Oxygen also, we have 2 atoms of oxygen here. So 2 times Z. So we have 2Z equals to, you have 2 oxygen here attached to the carbon dioxide. So this gives us 2 times 2A. So that gives us 2A. Plus, again, we have oxygen, 1 oxygen attached to the water. 1 oxygen attached to the water. So this is a plus B. So now if we already know A to be 4. So now we put into the equation. So then we have 2Z equals to 4A. So this will give us 8 plus 5. So means that Z equals 2. So this implies that Z equals to what? 6.5. Because you have 2, Z equals to 13 divided by 2, which is 6.5. So that's the equation, or that's the value for Z. Okay. So now, so I'm going to change this. Let me see. I will change this one for nitrogen. I'll say let this one be, let's say Y. Okay. So if we look at the Y component also, or sorry, N nitrogen, nitrogen is also giving me, nitrogen gives me here at the left side, the reactant side, we have Z times 3.76 times 2. So this gives me Z. So that gives me Z. Z is, and we know Z is 6.5. So we have Z times 3.76 times 2 equals to 2Y. You understand? Equals to 2Y. Equals to 2 times Y. Okay, so if you solve this carefully, Z we know already to be 6.5. Okay, so Z equals to 6.5. So this gives me 6.5 times 3.76 times 2 equals to Y, 2Y. Okay, so if you solve this carefully, and the value for Y now gives you, Y will be equal to 24.4. That's the value for Y. Okay. So now, what you do is that now we know all the unknowns inside this equation. So now we are going to write the full equation. So now the theoretical equation now becomes C for H10 plus, now our Z is 6.5. So 6.5. Then we have the oxygen plus 3.76 nitrogen. This is for the air side and the air side. Then we have the for the carbon dioxide. What is A? A is A is 4. So 4 moles of carbon dioxide plus water. So for the water we have B, right? So B is 5. So 5 moles of water. So 5 kilomoles of water plus the nitrogen. So the nitrogen now gives us 24.7, sorry, 24.4. 24.4 24.4, okay, N2. Okay, so this is the theoretical equation. Okay, this equation now is the theoretical equation. And please pay attention, the comment I'm going to pass here. This 6.5, this is the exactly the theoretical amount of theoretical amount of air needed for complete what? Combustion of what? Of the fuel. Because what are the conditions for complete combustion? You see, we have carbon dioxide. All the carbon is converted into carbon dioxide. Hydrogen is converted into water. And we have, yes, the oxygen. Yes, so, and this is the air. So we do not even consider that. Okay, so the hydrogen reacts with the oxygen to form water, and the carbon reacts with the oxygen also to form carbon dioxide. So for the nitrogen, it just comes in and goes out like that without participating in the reaction. So now the equation is balanced. So this is the exact amount of air which is necessary for this is a complete combustion because it has carbon dioxide, it has water and nitrogen. You understand? So that's the complete combustion. So now we want to write down the air-fuel ratio. So now the air-fuel ratio is given by theoretical air-fuel ratio. Air-fuel ratio equals to mass of air divided by mass of what? Mass of the fuel. And this gives me mass of the air. Mass of the air. Pay attention carefully. Here I've mentioned to you over here before during our discussion. What is the mass of the air? So mass of the air is given by, how much is this? So mass of air is 29 kilogram per kilomole. 29 kilogram per kilomole. So that's the mass of the air. So now we'll write down 29 points. So that gives us 29 kilogram per kilomole. Okay, but we need to multiply by the number of moles of the air present. You see, the number of moles of air that is present in the reaction is given by, we have 1 kilomole. Please pay attention to this thing that I'm giving information. I'll take this color. So we have 1 kilomole of oxygen here plus 3.76 kilomole of nitrogen. So for the air part, it is going to give us 4.76 kilomole of the air. Okay, then we multiply by 6.5. So this is going to give us 6.5 times 4.76. Okay, 4.76 kilomole of what? Of the air. So all divided by mass of the fuel. So mass of the fuel, we have, for the fuel, we have carbon So mass of the fuel consists of two. So we have carbon and hydrogen. Okay, so let's see again. Carbon is 12 kilogram per kilomole, and hydrogen also is 2 kilogram per kilomole. Okay, 12 kilogram per kilomole. Okay. So what we are going to do over here, we have for the fuel, the molar mass of the carbon over here is, you see, we have carbon. There are 4 of them. So we multiply by 12. So we have 12. One of the carbon is, the carbon, molar mass of the carbon is 12. But we have 4 of them. So we multiply by 4. Okay. Then plus molar mass of hydrogen is 2 kilogram per kilomole. But we have how many? That gives us, let me see over here. Yes, we have 10. We have 10 kilomole. So let me see. This gives me, wait there. And that gives us, okay, this is 4. This is times 12. Okay. See, it gives me. So for hydrogen, we have 10 atoms of hydrogen over here. So it's going to give us, so normally the hydrogen is supposed to be 1 kilogram. So they're supposed to give us 10. They're supposed to give us 10. Then we'll have kilogram per kilomole. I'm going to cross-check that later on. Okay, times the total molar mass, times the total number of moles of the fuel. Here we have 1 kilomole, 1 kilomole of the fuel. So this gives us 1 kilomole. So times 1 kilo of the fuel. So if you solve this carefully, you're going to get F fuel ratio equals to 15.5 kilogram of air per kilogram of fuel. You understand? Per kilogram of fuel. So that is the result of this particular discussion. Okay. So now the next question, the last part before we leave. 50% excess air. So this time around, we want to calculate, use the same procedure. But this time we want to use 50% excess air. So now for 50% excess air, let us see how the situation is going to be like. So B, 50% excess air. 50% excess air is the same as 150 theoretical air. (150% theoretical air). So what we will do is that we are going to write down the original equation for stoichiometric air. Okay. So now, yes, one thing also you should know. So this 50% SSL, I've told you this is 150%. Sorry, it should be 150%. 150%. So 150% theoretical air. And this is the same as 1.5. Okay, the same as 1.5 air. So what we are going to do is that we are going to write down the equation for the previous balance reaction. So we have C4H10 plus, okay, so 6.5 oxygen plus 3.76 nitrogen. This gives me the 4 molecules of carbon dioxide plus 5 molecules of water. Okay. Then plus, now, since we have 1.5 excess air, so we are going to multiply this by 1.5. We'll multiply this 1. Let me see. We'll multiply this. So 1.5. This is 1.5 times this. See, so we multiply. This is for the excess air. Excess air. Okay. So since we have excess air, whenever you have excess air, then it means it is going to represent itself in a form of oxygen as a product. So we have oxygen as a product, and then plus the final product, plus we have nitrogen over here. Okay. We have nitrogen over here. So now what we will do is that since we have told that the nitrogen does not participate in the reaction, it only goes in and comes, it makes things easy for us. For this nitrogen, we have how many number of moles of nitrogen? It is going to give us nitrogen. If you consider nitrogen, we have at the reactant side, we have 1.5 times 6.5 times 3.76. This gives me how much? 36.7 moles of nitrogen at the reactant. So we just put the same thing here, 36.7 at the reactant. Okay? So now it is the oxygen that we need to balance. And we have to represent it by, we'll represent it by Y. We'll balance the oxygen now. So balancing the oxygen, we'll have oxygen at the reactant. We have 1.5 times 6.5 times what? Times 2. This equals to 2Y. So if you do this carefully, you're going to get for the oxygen side, Y equals to 3.25. Okay. So if that is the case, then we will rewrite the whole equation, this time considering the excess air. So this gives us C4H10 plus, if you multiply 1.5 times 6.5, that gives us 9.75 of excess air. So oxygen plus 3.76 3.76 nitrogen. So 3.76 nitrogen. Oh, that it was wrong. So we have, and then the product side will repeat the same thing. Carbon dioxide is here, CO2 plus water, 5 molecules of water, H2. And now we know the oxygen already, plus oxygen 3.7, sorry, 3.225. So 3.25 of oxygen plus 36.7 of nitrogen. So this equation is for 50% excess air. So now air fuel ratio for 50% excess air is going to give us, is given by AF equals to mass of the air divided by mass of the fuel. So this gives me, I'll write down all the equation down. It's similar to what we have done the previous case. So I have 29 kilomoles, sorry, kilogram per kilomole of the air, okay, times 9.75 times 4.76 kilomole, okay, of the air divided by, now similarly again carbon is 12 times 4 plus, sorry, plus 10 hydrogen plus 10. So this gives us, so this is the kilogram per kilomole times 1 kilomole of the fuel. Okay, so eventually the air fuel ratio equals to 23.2 kilogram of air per kilogram of fuel. Okay, so that's the end of our discussion for today. Is there any question so far? Anybody, any questions so far? What we have discussed? All right, so I heard that next week is a holiday, the whole of next week. So I think then we'll meet after the new year then, okay? So I wish you all the best and take good care of yourself. And I'll give a short tazkira before we leave. Okay, so one of friends